So we are going to see the recurrence relation by Master's theorem example. Okay, the recurrence relation is given by t of n is equal to 4 of t of n by 2 plus n. So we are going to compare this recurrence relation to the with the standard recurrence relation, which is given by t of n is equal to a t of n by b plus f of n. Now compare this equation with this equation. Here t of n by b means t of n by 2, hence b is equal to 2. So we have got b is equal to 2. Similarly, the coefficient is a, here the coefficient is 4, hence a is equal to 4, hence a is equal to 4, and the n is the f of n, hence f of n is given by n. Now the solution depends on f of n, so we are going to compare this f of n with the standard f of n, which is given by what? This relation. Okay, so it is given by theta of n raised to k into log raised to p n. It is not a power of log of it, this is not similar to this. Okay, this is different, this is different. Log raised to p of n. Okay, it is not like log of n raised to p. Now hence, okay, so when we compare this f of n, okay, with this f of n, here the nth power, here just as n is there, n is to 1, so hence the k is equal to 1. So we got k is equal to 1, and here no log term is here, right? When f of n is equal to n, no log term is here, hence the power of log is 0. Okay, when there is no log term, then the power of the log p raised to n term is 0. Okay, so p is equal to 0. Hence we have got, when we are solving a recurrence relation for t of n, we need to know the a, the b, the k, and the value of p. We have got to know all these values. Now we are going to check the relationship between a and b raised to k. In when we check that, we will know under which case, case 1 or 2 or 3 this problem comes. Okay, so now the value of a is 4, and we are going to check the value of b raised to k. B is 2 and k is equal to 1, hence 2 raised to 1 is equal to 2. Here we can see a is equal to 4, b raised to k is 2, hence a is greater than b raised to k. Hence therefore it comes under the case a is greater than b raised to k, which we have seen as a first case. Okay, so when we go back to the, you can check by going back. When you go back to the case here, see, this is the first case where a is greater than b raised to k. So the solution is given by t of n theta. Theta is, you have to write n raised to, here the log is in the power, not in the multiplication. Log of a at base b. We know the a, we know b, so we are just going to put the values to solve this when n a is greater than b raised to k. So okay, so the solution is n into log of a at base b. We know the value of a is 4 and base is 2. We can write this 4 as 2 square, and we know that log of here the reason this is a log of logarithmic rule, that if at the base and at the power, if the element is same, then we just remain with the n. Hence it is a base and this element is same, then we are just going to remain with the power. Hence the 2 get cancelled and only this 2 remains, and the t of n is given by theta is equal to n square. Please remember this rule, you are going to use it often. Now second equation is t of n is equal to 16 raised to n t of n by 3 plus 1 upon n. Whenever you are going to solve the recurrence relation for this type for an algorithm or time complexity, then you are going to check if the conditions are satisfied. First check that and then proceed. Here a is equal to 16 raised to n. When we compare, n by 3 gives us b is equal to 3, and here f of n is equal to 1 upon n. Here when we compare this f of n with this standard f of n, here n is at the denominator. When we rewrite it, we can write it as n raised to minus 1. Hence this is equal to n raised to minus 1, as the power of n is minus 1. Okay, hence k is equal to minus 1. But we know that the condition for k is always greater than equal to 0. Hence this condition is not satisfied. Also, when we see a is equal to 16 raised to n, we cannot say that it can be greater than equal to 1. If the n is negative, then it can be less than 1. Hence when we say a is equal to 16 raised to n, it is also not a definite condition. Hence both of these conditions, a greater than 1 and k greater than 0, are not satisfied. Hence we can say that we cannot. So hence this recurrence relation doesn't satisfy the required condition of Master's theorem. Hence it cannot be solved by Master's theorem. So always check it for the conditions. Now we have seen the case of a greater than b raised to k. The second case is of a is equal to b raised to k, and there are 3 subcases in that. Okay, so we are going to take one example of each case. So when a is equal to b raised to k, we are going to check the value of p. If p is greater than minus 1, p is equal to minus 1, or p is less than minus 1. So let's take an example. This is the example. T of n is equal to 2 into t of n by 2 plus n log n. Okay, compare this with the standard equation. Here 2 is the a, here it is b, and this is our f of n, right? Hence a is equal to 2, b is equal to 2, and f of n is equal to n log n, right? Now we are going to check the condition of a and b raised to k. Here f of n is, first check this, f of n is equal to n log n. We are going to compare it with the standard f of n. Here n power is 1, hence k is equal to 1, and the log of n means log power is 1, hence p is equal to also 1. Now p is equal to 1, we have gotten a, and k is equal to 1, which is greater than 0, equal to 0. Hence this is also satisfied. So a and b raised to k, a value of a is equal to 2, right? From this equation we have got, and value of b is equal to 2, and value of k is equal to 1. Hence b raised to k is equal to 2 raised to 1, which is equal to 2. Therefore a is equal to, and b raised to k is equal to 2. Hence a is equal to b raised to k. Hence this example comes under which case? Second case. And also we have found that p is equal to 1, which is greater than minus 1. So let's go back to the case when a is equal to b raised to k and p is greater than minus 1. We are going to put the solution of the given time complexity is like this: n raised to log of a at base p into log of n log raised to p plus 1 of n. Okay, so the example is solved by, we're just going to put the solution is given by n raised to log of a at base p log raised to p plus 1 of n. Means the solution, we are just going to put the values of a and b, which is 2 and 2, and also value of p, which is 1. Okay, when we put all the values, we can solve it further. We know by the logarithmic rule, when 2 is there, only the power remains, which is 1. Hence here n raised to 1 remains, which is equal to n only, so we don't have to write it. So n into 1 plus 1 is 2, 1 plus 1 is 2, hence it is log square n. Hence the solution of the given time complexity relation is this. Next example, we have seen for a is equal to b raised to k, first case of p is greater than minus 1. Now let's see the second case. 2 into t raised by n by 2 plus n log n. Now whenever you get log of n at the denominator, or even n at the denominator, you have to take it to the numerator, and just you know how to do it. You just minus or negative, make the power negative by taking it to the numerator. So here 2 into t of n by 2 plus here n, this is divided by, it goes as multiplication, but here the power of log is 1, here it comes as minus 1. Okay, so we have rewritten this example in this way. Now from comparing it to the standard equation, this is our a, this is our b, and this is our f of n. Hence a is equal to 2, b is equal to 2, and f of n is equal to this. By solving for a and b raised to k, a is equal to 2, b is equal to 2, to find the k. Now just compare this f of n, this is f of n, right? This is our f of n with this standard f of n. Here n's power of n is 1, hence k is equal to, and nearest to k is there, na? So k is equal to 1, and power of log is minus 1, and here power is p, hence p is minus 1. Okay, so we got it. Now we are going to find a and b raised to k. A is equal to 2, b is equal to 2, which is we have gotten it from here and here. Okay, and k is equal to 1, which you got it from here. Okay, so now b raised to k is equal to, b is 2 and k is 1, hence 2 raised to 1 is equal to 2. Now a is equal to 2 and b raised to k is also 2, hence a is equal to b raised to k. So this is a example of second case, in which also p is equal to minus 1. We have seen it for p is greater than minus 1, now it is for p is equal to minus 1. So let's go back to the cases. Here for the p is equal to minus 1, the solution given by t of n is to log of a at base b into log of n. Here the power is p plus 1, here it is a log of n. Okay, so know the difference and remember the difference. Okay, now the solution is given by n is to log of a at base b into log of n. Just put the values of b and n, it is 2 2, and all the remains same. So as we know that this log by the logarithm, this is cancelling out, then only n remains and log of n. So this is our solution. Again, the next case is for p is less than equal to minus 1 in the second case. Okay, in t of n is equal to, this is our given relation. Rewrite the given relation. We will write it for what? This is at the denominator, so we are going to write it for the log to take this to the numerator. When we, it is a power 2, hence when we take it to the numerator, we are going to multiply it with the n and make the power negative, hence log of minus 2n. So 2 into t of n by 2 plus this. Now a is equal to 2, we are going to compare it with the standard one, so it is going to be a is equal to 2, this is our b, and this is our f of n. A is equal to 2, b is equal to 2, f of n is this. Compare this f of n with the standard f of n, which is theta of n raised to k log raised to p n. Power of n is 1, hence k is equal to 1. Power of log is minus 2, hence p is equal to minus 2. Here minus 2 is less than minus 1, hence p's value is less than minus 1. Also a and b raised to k, a is equal to 2 and b raised to k is equal to, we have found that k is equal to 1 and b is equal to 2. Put that value, 2 raised to 1 is equal to 2, hence a is equal to b raised to k. So where the solution of this type of problem is given by what? T of n is equal to theta n log of b, log of a at base b. Put the values of a and b, we get 2 2, hence it is going to cancel out and only remains the n, hence theta of n. Here please say, when I say cancel out, it cancel out as because the power of 2 is 1. If it was, if there is a situation where log of 2 raised to 2, suppose m, then the answer is n raised to m. Okay, when here is 1, we get it to n raised to 1, but which is equal to n only, hence we don't write that one specifically. Okay, but when the power is greater than 1, only the powers remain here and this all gets cancelled. But it is necessary to note that when this m is a power of this 2, not of the whole term, that is, it is n log of 2, log of 2 at base 2, log of 2 raised to m. Okay, it is n raised to log of 2 raised to m up at base 2, and not as a log of 2 and whole power m. For this it is going to happen, not for this. Okay, just remember that. Okay, now to the next point. Case 3 examples. In case 3, what condition do we have? A is less than b raised to k. Okay, so we are going to check it for this, and then if we are going to check it for p is greater than equal to 0 or less than 0. The given example is this: 2 into t raised to n by 2 plus n square. This is n square. Okay, now as usual compare it with the standard one. Here a is equal to 2, b is equal to 2, and the f of n is equal to n square. Compare this f of n with the standard one, which is n raised to k log raised to p n. Now k, the power of n is 2, hence here k is power, no? Hence k is equal to 2, and there is no log terms. When there is a no log term or any term, the p is going to be 0. Okay, because when is to log raised to 0 n, it is going to be 1 only, so the power is 0, hence p is equal to 0. Now let's check the relation of a and b raised to k. A is equal to 2, b raised to k is equal to 2 raised to 2, hence because k is equal to 2 and b is 2, that is a is less than b raised to k, hence we know the third case is a is less than b equal to. Also we have got p is equal to 0 also. So a is less than b raised to k and p equals to 0. There is a two condition in this matter: p is greater than equal to 0. So we are going to first give the same solution for p greater than 0 and p is equal to 0. So the solution is t of n is equal to theta of n raised to k log raised to p n. So the solution is this, right? So just put the values now. K is equal to 2, we are going to put it here. P is equal to 0 and the n. So as the log power is 0, the terms summarizes to 1. Okay, so only the n square remains, hence the solution is this. Now the second case, which is going to be p is less than 0 or greater than 0. Now this is our equation: t of n is equal to 3 into t of n by 2 plus n square upon log n. Again, whenever you get a log or n term at the denominator, may take it to the numerator. Okay, so we are going to rewrite it in this way: n square log raised to minus 1 n. Now compare it with the standard form. So we get a is equal to 3, b is equal to 2, a is equal to 3, b is equal to 2, and fn is this. Okay, so in the fn we see that the n, we know that n raised to k. Okay, so k is equal to 2 and log raised to p, so p is equal to minus 1. We got it. Now let's check a and b raised to k. As usual, a is equal to 3 and b raised to k is equal to, b is 2 and k is equal to 2, hence b raised to k is 2 raised to 2, so it is 4. So we get that a is 3, b is raised to k is equal to 4, hence a is less than b raised to k, so it comes under the third case. Now in the third case we have different cases also, so we can see that from here p is equal to minus 1, which is less than 0, hence the solution of the given, when we know that a is less than b raised to k and p is less than 0, then the solution is like 0 or O of n raised to k. So the solution is going to be O of n raised to k, where k is equal to 2. We have found it here, hence just put that k's value, O of n square. This is our final solution. Okay, then this last case or just an example: t of n is equal to 3 of t by 3 into t of n by 4 plus n log n. Take this example. So here the t of n is equal to 3 into t t of n by 4 plus n log n, and then they have given that t of 1 is equal to theta of 1. Find t of n up to 3 theta dot. Okay, now given the recurrence relation is given. Okay, so we are going to compare it with the standard form. We get 3 is equal to